Swayam Prabha. Digital India. Educated India.
Welcome to the lecture number 32. So, today we will continue with the gravity gradient satellite. If you remember, the last time we have derived the gravity gradient moment, it is given by 3 mu by r c whole cube times, here we have written E tilde, or it can be written in terms of E cap also. I will return back to this notation, cross I double bar dot E tilde b. So, if we are using this cross here, so if we are using the cross here in this place, so rather than using this tilde, we should write it this way. Okay. And the same thing, if you want to write in terms of tilde, so you can change it to r c whole cube E tilde b cross, and this cross, instead of this cross product, now we will put it here cross upside, which indicates a skew symmetric matrix. So, this part is your skew symmetric matrix. And then here we, instead of using I double bar, which is the inertia dyadic, we are just using the inertia matrix, and this will get converted into E tilde b. So, these are the notations last time we have worked out, and remember that E tilde b is the last column of the direction cosine matrix, which is C 1 3, C 2 3 and C 3 3. Okay. This already we have derived, and moreover, if you want to write the same thing in terms of E b, so rather than writing like this, you should write it as C 1 3 E 1 cap, C 2 3 E 2 cap and C 3 3 E 3 cap, where E 1 E 2 E 3 these are along the body axis direction. So, it is just a matter of whether you work with the this part. I will mark it here. This is your inertia dyadic, and this is your dot product. This part is your dot product, while here we are working in terms of the matrix notation. So, either of these two you can choose and you can work, but this will be more convenient once you have written this equation. So, it is much more convenient to work with this. So, we develop the whole thing right now. So, tau tilde g, then it can be written as 3 mu by r c whole cube and E tilde b. So, these components are here, these are the three components. So, 0 in the diagonal term, then here this minus C 3 3, C 2 3, and thereafter this place C 3 3 0, and then C 1 3 with minus sign, and here again minus C 2 3, this place C 1 3 and here 0. So, this is your skew symmetric matrix, which is here. Thereafter, put the inertia matrix, I 2 1, which is nothing but equal to I 1 2. So, let us write it as y 1 2 only, and I 1 3, because I 3 1 is equal to I 1 3. Okay. And this operates on this vector. So, this part is C 1 3, C 2 3 and C 3 3. This can be expanded and written in a proper format. So, this gravity gradient moment so, this final format I will write it here, or either one line at least maybe I will do it a single line. So, this is the first line, this will remain there, and then first multiply this matrix. Okay. So, we need to copy this here in this place, and this part then we will have I 11 C 13 plus I 12 times C 23, and similarly the second term will be I 12 C 13 plus I 22 I 13 times C 33, I 12 I 2 and I 23, this is I 23, this one here, this one should go here in this place. So, this is I 23, and the last one will be I 13 C 13 plus I 23 times C 23 plus I 33 into C 33, and operate on this matrix. So, we have to multiply these two matrices. Okay, so, if we multiply, we see that this is a matrix of size 3 into 3, and this is matrix of size 3 into 1. So, the result will be we get a column vector. Okay, if we multiply these two matrices, so we get a column vector. And that column vector, the first term, then once we multiply. So, here this is 0. So, if we multiply with this term, this will be 0, this term will count. So, minus C 33. So, this is minus C 33 times I 12 C 13 and so on. I 12 C 13 plus I 22 into C 23 plus I 23 into C 33. This is what we have written on here, I 22, I 23, C 33, C 23. So, this is multiplied by this and then plus C 23 times this last row. So, C 23 and the last row, then we have to copy, which is I 13 times C 13, I 13 times C 13 plus I 23 times C 23 plus I 33 times C 33. So, the middle term is here I 23 C 23, which is I 23 C 23, okay. And this can be organized. So, the delta tilde z, this will consist of this tau z, this will consist of tau 1, tau 2, tau 3. So, these are the three torque or gravity gradient moment or the torque components, and this is due to the gravity gradient. So, we put a g here. Okay. So, the first component of this only I am working out, and rest I just put it here finally. So, this can be arranged as I 22 times I23 I22 times C23 and C33. So, with this there is a minus sign. So, I22 C23 C33 with this minus sign appears. So, this particular term is inserted here in this place. Similarly, for the I33 term we have to pick up. So, I33 if we search, it is here in this place. Okay. So, for I33 C33 multiplied and then C23 is multiplied. So, you can see that C33 and C23 it is multiplied and this minus sign, that makes it plus. So, these two terms are combined together and written here. Similarly, the other terms we can fill in. You can just check it. So, this is your first term. So, what we see that once we are writing the Euler's dynamical equation. So, while writing that I1 we have written say there you have written I1 times omega 1 dot minus omega 2 times omega 3, this is equal to I2 minus I3, and on the right hand side you have written the torque. So, torque we have written by M1. So, in this equation if the off diagonal terms are 0. So, at that time we tend to write like this I1, I2 and I3. So, we see that if my off diagonal terms are 0 here. So, that is your I13 and this I12 and I23 these are 0. So, this will simply get reduced to this format, means this simply says that if off diagonal terms in inertia matrix are 0, okay, then this tau 1 can be written as, and here of course 3 mu by R c cube is there. So, 3 mu by R c cube and this term just we have to copy. So, I22 in that case it will get reduced to I2 and I33 we write as I3 and rest other things it remains same. In the same way, for if we have to write for the tau 2. So, you remember that I2 times omega 2 dot minus omega 3 omega 1 omega I3 minus this is I3 minus I1 equal to M2. So, on the right hand side the term that appears it will be exactly the same thing, here I2 minus I3, see here I2 minus I3. Okay. So, right side this moment equation we are writing. So, the moment term it appears like this. So, this you need not memorize, if you know how to write the left side. So, the right side you can write provided the off diagonal terms are 0. So, here from this place we see that this is I3 minus I1 and similarly, you just write C C, this is 3. So, write here 3, this is 1, write here 1 and this 3 belongs to, because your while we have worked. So, your if you remember that your gravity is acting along this direction, third axis of the orbital reference frame, that is EO3. So, in this direction your gravity vector is acting. So, therefore, in all of them this the second subscript it will be 3. you see here this is 3, here also this is 3. So, also here 3, also here 3, the same way the tau 3 this will be. So, here in this case this will be I 3 times omega I 3 times omega 3 dot minus omega 1 times omega 2, and then the other terms will come. Okay. Then we have I 1 minus I 2 and this equal to m 3. So, here exactly the same thing we have to copy, this is I 1 minus I 2, and similarly this 1 and 2 are there. So, we will put here 1 and here 2 and then just copy here this 3. Okay. And this one is with the off diagonal terms non-zero. So, this is applicable when I 1 2 not equal to 0, I 2 3 not equal to 0, and I 1 3 this is not equal to 0. So, for that case it is a valid. So, the other terms we can write here. This is I 2 3 times C 1 3. You can do the matrix multiplication yourself and check these terms. Okay, so, this case gets reduced to this case if the off diagonal terms they are all 0. Okay. So, this is very pretty simple to remember. So, our equation of the Euler's dynamical equation gets reduced to a simple format. Here we have inserted 3 mu by r c cube. Okay, you can see this term is here. So, this term is also present here, and rest you just have to put this C, which are the components of the transformation matrix, and right here this is 2. So, right here 2, right here 3, and then put just 3 3. This completes the Euler's dynamical equation when the gravity gradient torque is taken, other torques are absent. So, here only gravity gradient torque is present, other torques are absent. Okay. Now, what this C23, C33 all these things are, that we need to insert here in this place, and moreover this omega 1, omega 2, omega 3. So, as if you remember earlier we have discussed that this omega 1, omega 2, omega 3 these are not visualizable, because the itself the body orientation is changing, and about the body axis then the satellite is rotating. So, you cannot get out of the how the satellite is rotating. So, to describe that the Euler angle representation is required, and therefore, if you remember that we have converted omega 1, omega 2, first we wrote here like phi dot, theta dot and then psi dot, and this we converted to omega 1, omega 2, omega 3. This is omega 2 and omega 3. Okay. So, instead of using this notation, we use here theta 1 dot, theta 2 dot and theta 3 dot. These are the Euler rates. Okay. So, this is convenient in working in terms of theta 1, theta 2, theta 3, and then this is converted into the body x components of body axis components of the angular velocity. While these are the Euler rates along the 3 axes, but those axes are not mutually perpendicular to each other. Okay, and this whole thing we have derived earlier. So, I will not go into that again. Okay, so, you will just recall that if we consider the rotation to be given about the 3 axes, so this rotation is the first rotation is given about the third axis. This is the first rotation, then this is the second rotation, and this is the third rotation, which is given about the first axis. So, this sequence already we have studied, and we have seen that this can be written as C 2 C theta 2, where C theta it implies cos theta, and correspondingly the subscript S theta will imply sin theta. Okay, just will verify it. Okay, it is fine. If so, this theta 1, theta 2, theta 3, these are your Euler angles. So, these Euler angles, if you look in, so we have chosen to describe this. This is my EO3 cap. Along this direction, this is the satellite orbit. Along this direction, EO1 cap, unit vector along the velocity vector direction, and E cap O2. So, with respect to this particular orbital axis system, with respect to this system, your body is getting oriented. Okay. So, the body axis will get oriented with respect to this particular axis system. So, how that is getting oriented? It is getting oriented in terms of theta 1, theta 2, theta 3, these three angles. So, the first rotation you are giving about the third axis, the second rotation you are given about the second axis, the resulting second axis as we have discussed during the rotation, and similarly the first rotation, this third rotation is given about the resulting first axis. Okay. So, these are the three Euler angles. Now, if these Euler angles are small, means the cases where we can approximate sin theta equal to theta and cos theta this equal to 1. So, in those cases you can see that this gets simplified, c theta 2, c theta 3, because theta 2, theta 3 all these are small. So, a small angle approximation small angle approximation so this will become 1 c theta 2 theta 3, this becomes theta 3 because cos theta 2 will be 1 here minus theta 2, in this place s theta 1 s theta 2, these two multiply together. So, this multiplies like theta 1 theta 2 sin theta 1 and sin theta 2, and this is of second order. Okay. So, we ignore such terms. So, if we ignore, so this becomes 0, this part will become 0, and what remains there is this particular term. So, in this particular term c theta 1 is 1. So, here we get minus theta 3 only. So, here in this place minus theta 3. So, the same way if you look into this last term. So, s theta 1 s theta 2 both of them will multiplying together, that gives theta 1 theta 3 to the first order approximation. So, theta 1 times theta 3 again it is of second order. Okay. So, this gets eliminated, and from this place we get cos theta 1 equal to 1, cos theta 3 equal to 1. So, this gets theta 2 only. Okay. So, this way if you try to fill and look into the other parts also. So, this turns out to be a matrix where these diagonal elements will be 1 and the off diagonal elements will be opposite in sign. So, this is theta 2 minus theta 2 theta 3, then minus theta 3, here you will get theta 1. So, in this place you will get theta 1. So, we can check this term here, let us say this term we want to check. So, here s theta 2 and s theta 3, that becomes 0 multiplied together. So, this c theta 3 is 1. So, what we get here is minus theta 1. So, minus theta 1 is appearing here. Same way here in this place, this is just theta 1 times 1. So, here you get theta 1, and in middle term these are the three terms, that makes it theta 1 times theta 2 times theta 3, which is third order. So, we eliminate it, and what remains here this quantity only, which is 1 times 1. So, that gets 1. So, this way you can complete this matrix, and earlier if you remember, this we have written as an identity matrix minus theta tilde cross. Okay. So, where theta tilde cross is your skew symmetric matrix, which is nothing but 0 theta 3 with here minus sign. So, minus sign we are taking it outside. Okay. You will just you can check it here, this becomes theta 2, theta 3 0 minus theta 1 0. So, if you put it here and then you take the minus side inside. So, you can see that the resulting quantity will be the same as r. So, this r can be written in terms of I minus theta tilde cross, and this we have earlier proved while doing the rotation part. Toward the end we have done it. So, what is the benefit, that if the angle of rotation is small, okay, if your satellite is here and deviation from this orbital reference frame of the body reference frame, if it is small, so in that case that rotation can be approximated like this. Okay. You do not have to take the whole this matrix and then work out. So, this is the simplification. Now, the another part, that you do not have to memorize this matrix R. Okay. If you have to take larger angles, only then there is a problem that this matrix needs to be computed anyway. This matrix is it's a better not to memorize it, but rather compute it from time to time whenever it is required. Okay. When the angles are small, so it is very easy to remember, just use this r equal to this quantity. Okay. So, this gives you the resultant matrix, and now you can go back and do the job you want. Okay. Beside this, we have also proved omega 1, omega 2, omega 3. These quantities we have derived earlier. These are for the rotation, where we have given r 3 theta 3, r 2 theta 2 and r 1 theta 1. Okay. For these rotations, it is written here. So, these are not the transformation of the, this is not this transformation, this has come through some other transformation that I have shown you earlier, derived it earlier. So, this case also it can be simplified. So, this is 1 0, this is minus theta 2 0, this becomes 1, here this is s theta 1. So, this will become theta 1 and here 0 minus theta 1, and here in this part theta 1 theta 2. So, both are cos function. Multiplying it. So, this is theta 1 dot minus theta 2 times theta 3 dot, then this part theta 2 dot times, here this is 0, this is theta 2 dot, and then theta 1 times theta 3 dot. finally, the last one, this is theta 3 dot minus theta 1 times this one is theta 2 dot, which comes from here, and theta 1 times theta 3 dot, and this is theta 3 dot, and then theta 1 times theta 2 dot. Okay, so if we look into this, we are considering this to be small and these rates to be also small. So, if you approximate this, this can be approximated as theta 1 dot, theta 2 dot, and theta 3 dot. So, in your Euler's equation omega 1, omega 2, omega 3 was required. So, for a small angle, what we see that they can directly be replaced in terms of theta 1 dot, theta 2 dot, and theta 3 dot. The benefit of small angular displacement is that you do not have to worry about the order of the rotation you have taken, because as we have shown earlier in the rotation part, that the order of rotation for a small angle of rotation does not matter. Okay. Whichever order we take, we can always write in this way, which we have shown here in this place. So, this is the identity matrix, we will write it here itself, identity matrix or unit matrix. Okay. This is your unit matrix. And as usual, this is your skew symmetric matrix that we have written here. So, what we are trying to do here? We are trying to develop the Euler's dynamical equation in terms of Euler angles. As I have told you earlier that this Euler's dynamical equation, it is not a physically visualizable. So, to visualize this, we need Euler angle terms, but if you put the Euler angles in the equation of motion, Euler's dynamical equation, it becomes very complicated. So, here if we are approximating it, so in that case it gets simplified, and in most of the cases it will so happen that for a small angle deflection from the orbital axis, you will be working, because your satellite, you want to orient the satellite toward the earth. Most of the time what you will look for, that it is a earth pointing satellite, means this is my orbit, there is a satellite on which say there is a transponder or there is a camera, and this camera should always point toward the center of the earth. Okay. This may be one of the requirements. So, in such cases, if you have a satellite which can maintain its orientation along this direction, so it is a very good, and what we are looking for, that this satellite, once it gets disturbed from this particular position, okay, so it should be not deviating away from this position. So, that is what the part is, the stability is. Earlier we have also observed that the rotation about the minor axis is not stable if the internal energy dissipation is taking place. So, obviously, you have a satellite. So, there may be some vibration, it is not a perfect rigid body. So, always there will be some vibration involved with the system, and energy will start dissipating. So, we have to look also for the whether the satellite is stable or not, under what condition it will be stable. So, this is what we are going to work out here. Okay, so, finally, what is required, that in this orbit this is EO 3, EO 1, this is the axis we are using, and this is EO 2. Okay. So, this is the orbital axis system, and this system after some time, here somewhere is the center of the earth. So, after some time this axis will come here in this place. So, it is a rotating. EO2. Okay, so, as you can see that in the inertial frame itself, this orbital reference frame is having certain angular velocity. Okay. It is a rotating, right now it is like this. So, in the inertial frame it has rotated to this condition, and where the angular velocity is directed, it is directed perpendicular to the page coming out of this page from this place. Okay. So, as we can see from this place, this is your EO1 and this is EO3 direction, and this direction is vertically down EO2 direction, which is shown here. Okay. So, your angular velocity is coming out of the page, means the angular velocity of this orbital reference frame is along this direction, and that we can write as, let us say, omega 0. This is the orbital angular velocity, and if we put a arrow over this, so it becomes a velocity vector. So, the absolute angular velocity, which we write as omega, this is the absolute angular velocity. This becomes equal to how this frame is rotating, that is omega 0, and with respect to this frame, with the orbital frame, how your body is rotating. So, that we write as omega r, or either you can write as omega b. So, this is the angular velocity of the body axis with respect to the orbital frame, and this is the angular velocity of the orbital frame with respect to the inertial frame or inertial reference frame. Okay. So, to calculate this omega 1, this omega. So, what we have calculated here, this is just the relative angular velocity, because we have calculated it with respect to the, this is with respect to the orbital reference frame. Okay. So, we can put a, here I will not tag anything, because this is a general equation, while we are reducing it for a small rotation. So, we are, then we will tag it here, or either finally you can tag it, but if I put a r here, that means this becomes a relative angular velocity. Otherwise, omega 1, omega 2, omega 3, that will indicate your absolute angular velocity. So, coming to this place again, here omega, then your, this is omega 0, and in which direction this is? This is just opposite of the E2 direction. So, we can write here omega cap along the O2 direction with negative sign here, and plus omega r, which is nothing but omega 1, omega 2, omega 3, and we will be writing it like this. This is r minus So, this is E O2 means it is only along the second orbital axis. So, that means we will have 1 here and rest other will be 0 and put omega 0 here in this place. So, this can be written like this. Okay. So, this is still this whole thing what we have written here. So, what we have done, this is the angular velocity of the satellite with respect to the this term I will remove it. Let us first finish one thing, then we will take up this part. Okay. First we consider this part, this omega 0 minus E O2 cap. This is still along the. So, this omega 0 was actually oriented, this is taken, this is the orbital reference angular velocity of the orbital reference frame, but it is along the negative of the E O2. Okay. So, this is an inertial frame, but along the negative direction of the E O2, and therefore, the same thing we have written like this. So, this is along the orbital or in the orbital frame. This is still in the orbital frame and we need to convert it. This is in the orbital reference frame. And if what we are doing, that we are expressing the angular velocity along the body axis. Okay. So, we have to express the angular velocity, express the angular velocity. So, these are the angular velocity components with respect to the orbital axis, this particular part. Okay. This R stands for that, again reminding you. Okay. So, but these components are taken along the body axis. So, express the angular velocity, expresses the angular velocity along the body axis, but here this is not along the body axis. So, therefore, we need to convert it. Okay. Once we do the conversion to the body axis, then our job is done. Okay. So, we will continue with this in the next lecture. We wind up it here. So, thank you very much for listening.